All right, guys, this is our last lecture video. Let's start out with some review. Which of the following has a higher boiling point, pentane or neopentane? And so the thing to recognize here is that they all have CH bonds. We know CH bonds are non-polar. They have a delta electronegativity of 0.4, and they have the same molar mass, right? They both have 5 carbons there and the same number of hydrogens. But right, one is looking much more like a ball, much more like a sphere, and the other is looking much more like a line. And so this is going to have more intermolecular forces. That one is going to, pentane is, that one's going to have, therefore, a higher boiling point. More interactions between a line than 2 balls, okay? Harder to get to the gas phase, higher boiling point. Name the intermolecular forces, the IMFs, in compound A and compound B. Well, all of them have London dispersion. All molecules do. All molecules do. So London dispersion for both. And what about dipole-dipole? Well, we have a carbon-oxygen bond. And so if you calculate the change in electronegativity there, you will have a dipole there. Oxygen has an electronegativity of, again, you would look this up on a chart, as I'm doing right now, 3.4, and carbon has 2.5. Okay, so that's a delta of 0.9. So that's greater than 0.4. So that's a polar covalent bond. So that's going to have a dipole-dipole. But notice that compound A doesn't have any of the OH, NH, okay, or FH bonds that you need for hydrogen bonding, okay? In red here, you can see the hydrogen bond for compound 2. So that's going to have all 3. It's going to have dipole-dipole, and it's going to have hydrogen bonding. All right, so that's that one. One last topic. Now we're going to connect our heat. That was just some brief review. Our discussion of heat and calorimetry with now melting and freezing things. So if you think about what happens, like if you have a block of ice and you heat it until eventually, you know, it's going to melt, and then that liquid's going to boil, right? And eventually that steam is then going to heat up even more. But the temperature profile is pretty interesting. What you're going to see is the ice is going to heat up. And once it's an ice, once it starts to melt, it's going to not heat up anymore. This is the crazy thing. It's not going to heat up anymore until it's all melted. Because it takes heat to melt it. So it's absorbing the heat until it's all melted. Once it's all melted, then that liquid can heat up. And that liquid will keep heating up until it reaches 100 C, if it's at sea level, right? 1 atmosphere pressure. And then it'll start to boil. And a little bit of start to boil. And it won't boil until, it won't continue to heat up. It will be 100 C, the liquid gas mixture, until it's all boiled away. And then once it's all steam, if you continue to heat up the steam will heat up and get hotter than 100, go to 101, 102, right? So when you're boiling a pot of water, that's at 100 C, no matter how long you've been boiling it, okay? Still at 100 C, because it's taking heat to convert it to liquid to gas, all right? And so it takes a certain amount of energy to do that, amount of enthalpy, right? Delta H. And we can sum up the delta H's if we wanted to calculate different things, like the amount of heat to warm the ice to its melting point, the amount of heat to melt the ice, the amount of heat to warm the water, the amount of heat to boil the water, and then the amount of heat to heat up the steam, okay? So you're going to use Q equals MC delta T for these slopes, as we've done before, the slopes portion, but you're going to use something called the heat of fusion, okay? That is telling you how much heat it takes to melt something. And also heat evaporation is telling you how much heat it takes to boil something, okay? All right, so this problem is kind of a granddaddy of a problem, but we're going to do this. How much heat is required to evaporate 50 grams of ethanol at minus 10 degrees centigrade and heat it to 95 degrees centigrade? So in order to do this, what are we doing? We have a heat curve. It's starting at minus 10. This is T in centigrade, okay? And it's going to go up to, okay, it's what state of matter is? Well, it's already melted. It's a liquid. So this is telling us it's a liquid, okay? Because it's minus 10 is greater than minus 114. It's already melted, but it hasn't boiled yet, so it's not a gas. So we're going to have to heat it up to 78 to its boiling point. Then at 78, it's going to take some energy to boil it. And so the temperature is going to stay constant while it boils. And then it's going to go up and heat up to 95. Okay? So that's kind of our heat curve. And so for the first part of this heat curve, in blue or in green, we're going to use Q equals MC delta T. Calculate the heat. So we want Q, we want heat. We have 50 grams given to us. The heat capacity of liquid ethanol is given to us is 112 joules per mole, unfortunately. Okay, so that means we're gonna have to take this 50 grams and convert it to moles because it was given to us in moles. So let's go over here, 50 grams of ethanol. Ethanol, we can look this up, is the formula C2H5OH. And so the molecular weight of ethanol is going to be 12.01 times 2 plus 6 hydrogens, 1.008 plus 16 for the 1 oxygen. So if we add all that up, I'm just doing that right now, that's going to get you 46.06 approximately. 46.06 grams per mole is molar mass stuff, guys, right? So for every 46.06 grams, there's 1 mole, okay? So essentially we have 50 divided by 46.06. So we have 1.09, I'm gonna say 1.086 moles ethanol. Okay, so I'm gonna go up here and actually erase this and put that back in moles now, 1.086 moles. So now my units will cancel. And then my delta T, well, I'm heating it to 78 degrees C. I need to heat it to boiling minus 10 degrees C, right? So that's gonna become total, that would be 88 degrees C change. So 88 degrees change times that 1.086 times the heat capacity, 112. 88 times 112 times 1.086. That's going to get you Q equals 10,703 joules, right? And we want this in kilojoules, our final answer, but it's not the final answer. And we remember that for every 1,000 joules, there's 1 kilojoule. And so that's going to get us 10.7 kilojoules. So that's the green part. Now let's do another color for this part. That is the heat. We're going to have to use the heat of vaporization. We're vaporizing it, right, guys? So it's a certain number of kilojoules per mole. So this is just going to be Q times our mass times our delta H vaporization. It's actually now our mass is now in moles because we're given this all in moles, but it's moles, we know, times 38.6 kilojoules per mole. Okay, so if we do that out, we're gonna get 41.9 kilojoules. That's how much heat it takes just to vaporize all that. Okay, and now we're gonna go to this last portion here where we're gonna heat it up. It's at 78 degrees C, it's all vaporized, and now we're gonna heat it up. So again, this is MC delta T. It's a different C now because it's the heat capacity of the gas, okay, because we're heating a gas now. But we know the moles, we're giving everything in units of moles, so that's why we had to be in moles. 78.3 moles per joules per mole centigrade, and we're going to 95 degrees C, and we're coming from 78 degrees C. So that's going to be 1.086 times 78.3 times 95 minus 78. That gets us 1,446 joules, which equals 1.446 kilojoules. Okay, so we have our three portions of our heat curve. Now we want Q total. Q total is equal to 10.7 kilojoules, the three portions, just adding these up, plus 41.9 kilojoules, plus 1.446 kilojoules. And so that final answer is 41.9 plus 1.446, 54.0, or we'll just call it 54 kilojoules of heat would be needed. So you saw it's basically a three-part problem. It's not hard, but you just need to conceptually know what's going on and know that, hey, when ethanol is boiling, it actually isn't changing temperature. So staying at 78. So draw the curve, the heat curve, and you should be good. All right, guys.